In this lesson, we'll discuss the application of regression algorithm with R programming through a financial market case study. This includes modeling security price data with single and multiple features. First, we'll train the algorithm using the training dataset and examine various goodness of fit measures. And next, we'll test the algorithm on test dataset and examine its out-of-sample prediction efficacy. In this video, we'll introduce ABC stock price case study, which entails forecasting stock prices using regression algorithm. Please note that stock price prediction or stock return prediction is an attempt to determine the future value of a company based on analysis of factors which impact its price movement. There are a number of factors that help in predicting stock prices. These can be macroeconomic factors like state of country's economy, growth rate, inflation, and so on. There are also other factors that are more specific to a stock like profit margin, debt to equity ratio, sales, and so on. Let's examine the data provided in this case study. So we are given data for market prices of a company ABC along with Nifty and Sensex. These are market indices that represent broad market-wide movement of securities, and we are also given data of dividend announcement and a sentiment index. Let's discuss this data in more detail now. Think of a portfolio manager who has to build a model for a particular stock, which is ABC in this question and under consideration. The manager wants to predict the ABC stock price return for this stock using regression model. The data provided to us starts from 2000 and goes till 2019. So we have approximately 19 years of data. We can construct daily returns as provided here. So we have daily returns of ABC. These are provided in this column. And next, let's call it column B. Next, we have daily return on Sensex. This is column C. And daily return on Nifty in this column. Please note that Sensex and Nifty are Sensex and Nifty are two main stock indices used in India. They are the benchmark Indian stock market indices that represent the weighted average of the largest Indian companies. So Sensex represents average of 30 largest and most actively traded Indian companies. Similarly, Nifty represents a weighted average of 50 largest Indian companies. Another variable here is dividend announcement, which is provided here in this column. This variable attains a value of 1 if the company has announced a dividend on a particular date and 0 otherwise. So for example, if the value is 1 on this given date of 10 January 2000, because the company ABC announced a dividend on this date, and it is 0 for other days, as we can see, when the company did not announce any dividend. Please remember, this is a dummy variable. Lastly, we have sentiment variable in this column. It is a sentiment score that quantifies how investors feel about ABC company. It can be based upon news analysis or upon option market analysis or based on some survey of investors. We would not go into details of the construction of this score here and take it as given. A very high sentiment score represents bullish emotions of investors and vice versa. To summarize this video, in this video we introduced ABC case study problem with respect to stock price forecasting. We discussed the background of the case study, its relevance and implication for financial markets. We discussed the variables and data provided in the case study, the interpretation of each of the variable and its implication for the regression modeling. In this video, we'll introduce the problem statement with the ABC case study. The problem statement will be demonstrated and implemented with the R programming. In the first part of our problem implementation, we'll start with the simple linear regression model. We'll start the study with data visualization. We'll plot the returns and cumulative returns for ABC stock and market indices like Nifty and Sensex. Then we'll segregate the data into test and train dataset. We'll train and build the model using the simple linear regression algorithm, using market index as the independent variable and ABC returns as the dependent variable using the training dataset. So we'll train the model first. Then we'll evaluate the model with various goodness of fit measures and through visualization. Thus, we'll test the model, and also as a part of testing the model, we'll evaluate the out of sample model performance on test data set using various quantitative measures and also with visualization. In the next set of implementation, we'll employ multiple linear regression algorithm. We'll start with training and building the model using multiple linear regression algorithm, using market indices, sentiment, dividends, among other variables with the training data set. Next, we'll evaluate the model with various goodness of fit measures and through visualization. There are several issues that we'll deal with. These include multicollinearity, heteroskedasticity, and autocorrelation. We'll examine these issues and we'll try to find ways to resolve them. We'll answer the question how to resolve these issues in the estimation, and then we'll evaluate out of sample performance on the test data set using various quantitative measures and also with visualization. To summarize this video, we discussed the problem statement that will be implemented through R programming. In this video, we'll start with our implementation of ABC case study regression problem. We'll start with the ABC case study problem. We'll conduct the following steps. First, we'll load the relevant packages. In this case study, we are going to use read Excel package. This package will help us in reading Excel files, data in the Excel format. We'll make use of lubridate package, which will help us in date time manipulation. Then we'll use moments package for understanding various properties of data. Then we will load car package along with LM test will help us in various regression related aspects. And lastly, we have sandwich package that will help us in handling the estimation related issues in the regression. So with this, now we have loaded all the relevant packages. As a next step, we'll set our working directory. Please remember it is always a best practice to set the working directory. In order to set the working directory, we'll go to this session button, set working directory, go choose working directory. We have this particular file and folder. If I put on open button, notice a command appears on my console window. This command suggests that now that this command is run, appropriate working directory has been set. So for reference, I'll just copy paste this command on my code. So now that my working directory has been set, I can read the data file. So data, I will use read Excel command. The file name is abc.xlx. You can save it with any name. I have the file in with the name of abc.xlx. So now the file is saved. You can check a few initial elements of the data file by using head data command. Notice there's a date variable, there's a price variable, a return variable abc, sensex returns, dividend announcement dummy variable 01s, sentiment variable, and nifty, as we have discussed during the case study problem statement discussion. You can also check the dimensions of this data with this dim data command. It has 5,153 rows, that means 5,153 daily observations for 7 variables that we just saw. One important issue to be noted, you can check the class of various elements. For example, if I want to check the class of date variable, let's see. So I put dollar symbol, which means I am accessing the variable inside data frame. So it's already a date variable. Also, please note there is a time element, which is a spurious kind of spurious in nature, we need not handle this time element for now. We only need date, which means month, day, year. So I want to remove this particular aspect. I can do that very easily. I can simply just run this date, data, $date, and I can change the convert type to date. Earlier it was in POSIX-CT type of class, which includes not only date but time element. Since we are making use of only date element, I'll simply convert it to the date part. So now if I run this, notice the time element is eliminated, only date is there. I can run this class command again, so its class is date. So now it's not anymore the POSIX-CT element that it was earlier. Now it's only purely a date element. So to summarize this video, we set the working directory, we load the relevant packages, and then we set the working directory. We read the data file, which is abc.lx, in our data variable, which is essentially a data frame. We can check that also. For example, you can type the class command and check the data frame. It's a data frame. Then we check the dimensions of this data. We converted our date variable from POSIX-CT datetime object to purely a date object. From the next video, we'll try to visualize the data with its relevant properties. In this video, we'll conduct the visualization of data. We'll visualize the data. We'll examine key variables. We'll conduct the visualization of key variables, including returns on ABC and the market variable, that is Nifty. So first let us plot the ABC returns. So we'll use the plot command. On the x-axis we'll have the date variable. On the y-axis we have the return variable. We'll give the x-axis name using xlab command as date. So this will give us the x-axis as date, and then y-axis label as, we'll keep the y-axis label empty, but we'll give them central heading. We'll use central heading or main heading as ABC returns. So we'll plot the ABC returns along with prices, and we would like to see the plotting format in the line form. So we'll put type as L. Now as soon as I run this command, we'll notice that a plot will appear on the plot window here. We can zoom it. You can see the plot. You can see there are some extreme falls here around 2005 and 2008 and 10. Extreme down movements, increase in volatility. If you want, you can export this plot to save as image. You can use different image formats to save this plot. For example, you have PNG, you have JPEG, TIFF, various formats available to save. Also, you can export it in the form of PDF. You can save it as PDF, or you can copy it to clipboard and then paste it on Word document and PowerPoint presentation and so on. So this is the return variable, ABC returns. Next, I would like to plot the cumulative returns on ABC. So how to compute cumulative returns? Let's name this variable as CUMRET. So we would like to plot this cumulative return variable. The simple way to compute cumulative returns are use data $price. This will use the price and divide it by the beginning price, opening price. So any price divided by its opening value will give us the cumulative returns here. So I need to use the first value of price, and then I subtract it from 1 to reflect the return aspect. So this will compute the cumulative return in my data cumulative return variable. Now I need to simply plot it. So I can use the plot. Again, I can simply copy paste the command that I used earlier, the same command, only that now instead of writing as ABC, I can use this new variable CUMRET, cumulative return variable. I can use that and then name the plot as cumulative returns. And if I run this, the cumulative returns, you can see the cumulative returns provided here. So it looks like this. There is a sharp fall around here, 2005. These are cumulative returns. Now we'll plot the market return. So we'll plot the Nifty returns, market or Nifty returns. Very simple. I don't have to do any extensive coding for that. I'll simply use my plot command that I wrote earlier, and instead of using ABC, I will do a minor change here. I'll write Nifty, so this will give me the market return Nifty, other things remaining the same. I'll use the, instead of ABC, I'll change the central heading to market returns. And now if I run this command, notice these are my market returns. So these are simple market returns. Next we'll plot the cumulative market returns. Cumulative market returns. I have to just write a very simple command, which is data dollar cumulative. This time around we are computing Nifty cumulative, so I'll use this, and the very simple sum command, cumulative sum command, to compute the cumulative Nifty returns. This will provide me with the cumulative Nifty returns, and I will not write the command again, so I'll just simply use the same command that I used earlier, and I'll just change here cumulative return. Instead of cumulative return, I'll use cumulative Nifty returns, and in the central heading I'll change the name to cumulative market returns. So here I can see the behavior of cumulative market returns easily. This is the behavior of cumulative market returns. To summarize this video, in this video we conducted basic visualization of return variables. This included ABC returns and Nifty returns. We also plotted the cumulative returns. In the next video, we'll conduct the summarization of data. We'll provide some summary measures. We'll also have a look at the normality, skewness and kurtosis of the data, and stationarity of the data as well. In this video, we'll discuss the basic properties of our data. We'll start with a very basic summary measure. So we'll start by summarizing the data. For that we'll use summary command, simply summary command. And for summary command for ABC returns, we can see how ABC returns are distributed. The minimum value, which is quite high, and the maximum value, and first quantile, which is 25%, median value, which segregates the data between two halves, then mean of the distribution, and 75 percentile of the data. So these values are provided. Similarly, I can examine the summary of Nifty market index, which is this. So here also we can see extreme return, which is minus 14%, maximum is around 15.97, which is 16%, and same matrix, that is first quantile, median, mean, and third quantile. In the next step, we'll conduct a very important operation. We'll try to see the probability density of our data. In R, the same can be implemented with this plot command, and then density data dollar ABC. So this will plot simply the density of ABC, but we want some aesthetic aspects also. So we'll type main as we'll type here as density. This is a density graph. So we'll type density graph, and then we'll name the X and Y axis. So X axis will just name simply the data. Also, we would like to, since we are plotting the density for both market and ABC, we will try to give them different colors. First, we'll plot the density of stock ABC return density in red. Let's give the line width of 2, so it will plot a slightly more solid line. Line type as 1, so a more solid line will be there. And we probably will, if you do not specify, the limits can be extremely large, so we'll restrict the limits of x-axis to minus 0.6 to 0.6. Although these will change depending upon your final result. You may modify and tinker with that a little bit here and there to improve the aesthetics. Next, with this lines command, I do not want to plot a new graph. On the same graph, I want to plot Nifty return, so I'm using lines command, Nifty. Then I would like to specify the color. Earlier I have used the red color to plot the ABC return, so I'm using the blue color to plot the Nifty returns. And line width, again I'll use the line width of 2. So this will be plotting the density of Nifty, and then I would like to add a nice legend on the one side. So in order to check this, first let me plot the, okay, so this is my plot of ABC return, then my density plot. In blue we have Nifty. So now there's some empty space on probably the top left, so I'll use that space to put my legend here. So top left, and I'll use C, ABC. Then I'll name the next legend as Nifty because of this sequence. Since ABC is in red, so I'll use the red here, and Nifty is in blue, so I'll use the blue here. And now I'll run the legend. So if I run this legend, a very nice legend will be added. Use fill equal to color, and now the legend is added. Let us enlarge this plot a little bit. So notice on this plot ABC is plotted in left, and notice the behavior of ABC. It is extremely left skewed. You can see the extreme left tail of ABC, while Nifty is rather more balanced and symmetric in blue. Nifty returns are more symmetric over the sample period, while ABC, which is in red, are extremely skewed towards the left. That means there are extreme negative returns, which we also saw in the summary measure. So it is sort of confirmation of that. To summarize this video, we first summarized the Nifty and ABC returns using summary command, and then we plotted their density distribution to understand the basic characteristics of our return data for ABC stock and Nifty. In this video, we'll examine the normality and stationarity of the data. Now, first, as a part of normality examination, we'll start with the skewness of the data. We'll write skewness data dollar here. So we'll compute the skewness, which is very high negative, as we already saw in the diagram. The skewness of ABC is extremely left skewed. Then we'll examine the skewness of Nifty returns. So the Nifty is also negatively skewed, but the skew is not very high. But we want a slightly more solid evidence for that. So we'll conduct basic Agostino test of skewness. So we'll type data dollar ABC, and this will provide a more statistical measure. And notice that it provides you with a p-value which suggests that the skewness is statistically significant, in fact very significant for ABC returns. Similarly, we can compute the skewness of Nifty returns. So here we computed the skewness of Nifty returns. This is also in terms of magnitude not very high, minus 0.177, but its significance is quite high. So this is also slightly negatively skewed and low in terms of magnitude, but reasonably higher in terms of statistical significance. Now, skewness is a measure of asymmetry on the left side or right side. In the remaining part, we'll discuss the kurtosis measure. So we also examine kurtosis measure. Kurtosis is a measure of peakness and tail. So how peaked or less peaked as compared to normal distribution, and how tailed it is, whether tails are fat or not. So first we'll compute the kurtosis of ABC returns. The kurtosis is quite high. We'll also measure the kurtosis of, probably this can be accounted to the extremely fat tails of ABC and the peak nature, as we saw in the density distribution. Nifty also has a very high kurtosis, so we can see that it also has a very high kurtosis. Normal distribution has a kurtosis of 3. So as compared to normal distribution, the kurtosis levels are very high. Now we would like to again have a slightly more statistically significant evidence, so we'll use the Anscombe test. First we'll compute it for ABC returns, $ABC for ABC. Okay, so the kurtosis is not equal to, in fact very significantly different from 3 for ABC, which we expected. We'll also see the kurtosis. Kurtosis is the measure of peakness and tail, how fat tails are or how peaked the distribution is. as compared to normal distribution. So the tails are fat and the pigness is very different from normal distribution. Here also kurtosis is very significantly different from normal distribution. As a final test, we already know although that skewness and kurtosis are very different, and as a combination skewness and kurtosis decide whether data is similar to a normal distribution, the bell-shaped curve that we discussed. As a final test, we would like to have Harke-Bera test, or it's called Harke-Bera test or Harke test, which will give us a sense of its normality, although we already know that data is not normal, but it's still a combined measure of normality, which is very high, which is much greater. So data is non-normal. As you can see, this is a combination of extreme skewness and peak nature of ABC. Although in case of Nifty, the skewed nature was less. It was not as skewed, but still as compared to normal distribution, it was skewed. And the tails were fatter on both sides as compared to normal distribution. Same for Nifty as well. Nifty, we can see it was symmetric, but still it's non-normal. Now normality is high. We'll see while working with the regression model, we'll see how to deal with these issues. But we have seen the summary measures. Now just to summarize this video, we computed the skewness, kurtosis and normality of the data, overall normality of the data. We found that ABC was extremely left skewed and both of the distributions have fat tail as compared to normal distribution and higher peaks. This was statistically examined using Agostino's test and Anscombe test, and using Harke-Bera test we also examined the overall normality of the data. We found that both the series ABC return series and Nifty return series are non-normal in nature, and the result is statistically significant as well. In this video we'll discuss a very important property, that is stationarity of the data. Stationarity of the data refers to the fact that the mean and standard deviation or variance, as we have already discussed the concepts, these are changing with time, and if these parameters such as mean and variance are changing with time, estimation is fraught with various econometric issues. So before estimating any kind of relationship, it is important to know whether your data is stationary or not. There are three very useful tests for that, and these are augmented decay Fuller test, Phillips-Perron test and KPSS test. For these tests we need to load a very important package, which is URCA, unit root test. So we'll load this package URCA, and now we'll start with our, first we'll conduct the augmented decay Fuller, or often called ADF test. The command is quite simple. We'll write summary and ur.df for augmented decay Fuller, df data $ABC is our price series. So we'll use ABC, and notice the null hypothesis of this particular augmented decay Fuller test is that data is non-stationary. Since notice the test statistic, it is minus 51.7, which is much lower and much higher in terms of magnitude as compared to 1%, 5% and 10%. Therefore, with a lot of confidence we reject the null and we say that data is stationary. Please note, this is a non-stationarity test. That means null hypothesis of this is that data is non-stationary. Very similar syntax we'll use to check the stationarity of the Nifty returns. If the returns were non-stationary, any model such as regression algorithm will be difficult to estimate properly. So we'll check the Nifty returns also. Nifty returns also, notice that we reject the null of non-stationarity with a lot of confidence. So again the data is stationary. But while testing stationarity, it is very useful to test through a number of tests. So for example, augmented decay Fuller tests were tests of non-stationarity. Here we'll be using tests such as PP test also. Look at the test such as ur.pp, and notice here again this is also a test of non-stationarity and we reject. Notice the test statistic, which is very large in magnitude, very negative as compared to the standard statistic. Given the large test statistic, we can reject the null and again say that data is stationary. So here also the null was of stationarity, so we reject the null and we say that data is stationary. It is very high tested statistic, so we are again and again saying that data is stationary. Another very interesting test, and generally it is required to test through stationarity test also. So earlier, both the tests earlier that we did, Phillips-Perron, augmented decay Fuller, they were test of non-stationarity. Now we'll make use of KPSS test, which is the test of stationarity. So first we'll run the KPSS for ABC returns, and notice the test statistic is much lower than 1%, 5% and 10% level. So data is, again, we are not able to reject the null of stationarity, so data is stationarity. Similar test we conduct for Nifty returns also, KPSS test, and here also we find the data is stationary. So we have conducted the stationarity test. To summarize this video, we conducted test of stationarity and non-stationarity. Here augmented Dickey-Fuller and Phillips-Pinot tests were tests of non-stationarity, where null hypothesis was of non-stationarity and rejection of null indicated stationarity, while KPSS test was of stationarity, and we failed to reject the null, which indicated again the stationarity of the data. In the next set of videos, we'll start with training and testing of regression algorithm and prediction of stock returns. In this video, we'll segregate our main data, which is ABC stock return data, into training and test data. Training data will be employed to train the linear regression algorithm, while test data is employed to test the out of sample forecasting efficiency of the algorithm. So we'll start the analysis by segregating the data into training and test data. As a first step, we'll create our train data segment, which is equal to main data, and we'll tell R that the date should be less than equal to. Now we'll filter the date with 2017, less than 2017, December. So 1st December 2017 is our cutoff point, and this is the maximum, and it should be great. Let's say we also filter observations before 2006. So let's say we also do not want to go too early, so we filter those observations that are for which the year is greater than 2006. So we are filtering from 2007 to almost 2017. We are filtering all the observations. So this is our train data, and let's check this. So we'll check the head of train data, head of train that starts from 2007, as we can see here. Let's check the tail of the train data. It ends with 2017. As we can see here in the date segment, we can see on the console window it ends with 2017. And if you look at the dimension of the train data, it has 2850 observations. Similarly, we'll select our test data. Our test data is again in a similar manner. We'll filter it. Data $date should be greater than, and now this time around we'll use the exact same date criteria, which is greater than as dot date, and we'll precisely select the date that we selected earlier. We'll select the same date, in fact. So all the observations with higher date number will be taken here. So now this test data will contain the remaining observations that are above 1st of December 2017. Let's examine this. So the head of the test data starts from 2017, in fact 4th of December, and look at the probably 2nd and 3rd are holidays. And if you look at the tail of this, tail of the test data, the tail, it ends with 2019. And if I examine the dimension of test data, so around 478 observations to test the algorithm. So to summarize, in this video we segregated our data into two segments. First, the training data, which starts from year 2007 and ends at 1st of December 2017, while the test data contains the remaining observations starting from 4th of December 2017 up till 2nd of October 2019. In this video, we'll train our simple linear regression model by regressing the ABC returns on Nifty returns. So we'll model simple linear regression model by examining the ABC returns and Nifty returns relationship. So in R, this relationship examination is done with a very simple LM command. So we'll run this LM command, which indicates some kind of linear regression model is about to take place, and where we are regressing ABC returns. Here this notation suggests that ABC is the dependent return variable, ABC returns, and the independent variable is Nifty. Our data is train data we are using to train this linear regression model, and the output of this linear regression model, the train model output, the coefficients will be stored in SLR object, simple linear regression. Let us see the summary of this object. We'll assign the summary to the model object, summary SLR. Let's have a look at this summary variable. I can simply extract this by printing model. Notice the console window. On the console, we can see the printed output. In the output, the following objects to be noted. First, note the coefficient of Nifty, which is 0.397. This is also the measure of beta that we have discussed. Recall the discussion on beta, that beta represents the sensitivity of ABC returns here. That means if market moves by 1%, ABC stock returns move by 0.39%. Also notice the t-value of the coefficient, which is heavily significant. Remember, this t-value is computed as the ratio between estimate, which is the coefficient, that is 0.397 here, divided by the standard error. Now, this t-value 18.67 is very significant. The 3 stars suggest that it is even significant at 1% level. Recall our discussion on the significance levels. Null hypothesis here is that this coefficient Nifty has a value of 0, which means Nifty does not affect the movement in Nifty do not affect the returns of ABC stock. However, given this result, the very high significance of this result at 1%, we can say definitely there is a positive impact of Nifty, that is market movement, on ABC returns. Here it appears if market moves by 1%, ABC stock moves by 0.39%. And this relationship is statistically significant at 1% level. So we are very confident. In fact, we are more than 99% confident that there is a relationship between Nifty returns and ABC stock returns. Moreover, notice this adjusted R square here and the multiple R square. In fact, we'll focus on adjusted R square, which is a more improved version. It is 10.87%. This suggests that out of the total variation in ABC return, 10.87 variation is explained by Nifty, which means, and recall our discussion on the market risk and systematic risk, that almost 10.87% part of the overall risk, total risk, if total risk is 100%, 10.87% part of the risk is market risk or systematic risk driven by the market movements. In this case, market is proxied here by Nifty. The remaining approximately 89.21%, around 89%, is the idiosyncratic risk, which is specific to ABC stock. The remaining 10.87% is driven by market and explained by market. So this is our interpretation of the overall regression. To summarize this video, we examined the relationship between ABC returns and Nifty returns by regressing ABC returns on Nifty returns. We also examined the output of this regression model. We discussed the coefficient, its significance, the idiosyncratic and systematic part of the risk associated with ABC stock return, and we have now trained our linear regression algorithm. In fact, this is a simple linear regression algorithm because we are using only one variable, which is Nifty. So now that we have trained our simple linear regression algorithm on the training data set, now we will examine the efficiency of this model in subsequent videos. We'll examine some of the econometric issues that this model may face and how to deal with them. In this video, we start with the residual diagnostics of the model. Residual diagnostics. First, we'll look at the density plot of the error terms. So we'll use density plot. Recall that we have already stored our trained model in the model variable or model object. So we'll simply use the model residuals. So we'll plot the density of this. Let's examine the density plot of residuals. Notice that while the shape of this density is relatively similar to normal distribution, however, its left tail is extremely long, which suggests that it is extremely skewed. We can also corroborate this by plotting the density plot of studentized residuals. For that, the command is simple. We can just write the same density plot and we type R student. But this time we'll pass on the original model as LSR object, which is the model object that we created. So again, it is also very similar. So the density plot of residuals and as well as studentized residuals is extremely left skewed. Students distribution is essentially t distribution. So these are standardized errors. And as we can see, it is extremely left skewed. Another test to examine the behavior of the model and its residual is QQ plot, which checks the normality. Let's examine the QQ plot. So we pass on the fitted object SLR, which we already fitted. We also would like to know some of the extreme observations that may create problems for us. So we'll give the number as n equal to 10. So this will identify 10 extreme observations for us. Let's see. So we'll run the QQ plot command. Also, we would like to see some of the extreme observations. So I'll type id equal to list n equal to 10. So we would like to highlight 10 extreme observations. I run this command and the model is plotted here. So we can see the quantile wise distribution of studentized residuals. So the residuals are plotted and we can see this number of observations that are extreme. Observation number 72, 152 and 2544. These are some of the extreme observations that depart from the normality. These on the fitted model, these observations are plotted along the fitted model. We can see the observation numbers. The studentized residuals are plotted here. We can see some of the observations plotted here. So this is, and we can see that most of the time the observations, the residuals are along the normal line. The straight line indicates the normal line. The observations that deviate from the straight line indicate deviations from normality. And we can see some of the fitted observations on the extreme left and right end. These some observations deviate from the normal distribution. Normal distribution here is represented by the straight blue line. Lastly, we can also conduct the outlier test. Now, there is a basic outlier test and it will also adjust for born for any values, adjusted p-values. Let's see them. So if I run this, notice unadjusted p, there are a lot of very significant unadjusted p-values, but once there is born for any correction, one can see the significance is less, but still we have there are 6 extreme values and these appear to be very similar to the earlier ones. So these are our extreme values. If you want to know more about these functions and their theoretical underpinnings, you can simply type question mark QQ plot and see the background, the entire background of these commands. For example, this is for quantile comparison plot to check the normality, and the outlier test also. You can check that. The theory behind these commands by running the question mark. You can read more and more about these commands. Lastly, if you feel that these observations are vitiating, these extreme observations are vitiating your estimation model, you can remove them from their model. You already have the observation numbers. You can remove them from the model and then run the model again to improve its estimates. To summarize this video, we created density plot of residuals. We also have examined the studentized residuals on the density plot. Next, we checked the deviations from normality with the help of QQ plot. And we also conducted the outlier test to see some of the outlier observations. We found that there are number of outlier observations that may vitiate the estimation. As a future course of action, one can remove these observations from the model, but please note sometimes these extreme observations also carry useful information, probably that may help us model extreme values representing extreme events. So sometimes it is not advisable to remove these values, so a subjective judgment call may have to be taken here. In this video, we'll examine a very important issue, that econometric issue that afflicts estimation, which is heteroskedasticity, which is the non-constant variance. So as an intuition, let me plot the fitted model SLR, and I'll plot the residuals with this plot command. Notice the behavior of residuals with the fitted values. Notice the variance as we go ahead with values, fitted values. Notice the variance is not constant. Sometimes it is high, sometimes it is low. And the way residuals are scattered around the fitted line, their variance seems to be not constant, which indicates that model may be afflicted by the issue of heteroskedasticity. To check it more formally, there's NCV test. If you want to know more about it, you can type NCV test and all the details will be provided to you. However, for now, for the non-constant variance, error variance, we'll simply run the command. So we'll type NCV test, and this is part of CAR package, CR package that we installed earlier. We need to supply it with the model object that we created earlier. So model, and first we'll try with the studentized, without studentized errors, and let's see. So let's see the output on the console. So I need to provide the fitted object actually. So instead of model, I need to provide the fitted object. Notice the p-value is very significant, which indicates, and this and simple NCV test fits the values along the fitted values, and it seems that when fitted along the fitted values, the error variance is not constant. It's varying very significantly, which is indicated by this very high value of chi-square and a very high significance level of p-value. So if you look at the p-value, it's quite high. We can also see if these residuals, they are varying with the nifty values. So we will specify the formula. This time around we do not want to see with fitted values, but we want to see with nifty. By default it runs with fitted values. This time we'll model it with the nifty, which is the nifty returns, and along nifty returns also we have a similar evidence. We can see that there is a very significant variance, residual variance, that is not constant. Another very interesting test of non-constant variance is BP test or Bruce-Pagan test. If you want to know more about this, you can simply type $BP test and all the details are there. So this BP test is a very interesting test of heteroskedasticity. It simply checks whether error variance is changing. So let us run the model BP test, and we'll supply the model object. Here we are supplying the model object, and we will decide whether we want this error terms to be studentized. So without studentized, again a very significant p-value, very similar to one we have earlier, which indicates a very high level of heteroskedasticity. If we studentize, let's see if we studentize the t values, error values, this time we are not able to reject the null of homoscedasticity. So when we are working with with studentized errors, probably it seems that the model is not afflicted that much with heteroskedasticity. However, when we are running this model, this test, BP test, Bruce-Pagan test, without studentized errors, then it gives us heteroskedasticity. So probably the issue is there. The issue of heteroskedasticity is slightly moderate in the sense that without student t values, it is not affecting our estimation. So just to summarize, we tried to visually examine the issue of heteroskedasticity. It appears to be the case that residual variance is not constant. However, when we conduct this using BP test with studentized errors, then our model seems to be not much afflicted by the issue of heteroskedasticity. So there is issue of heteroskedasticity, but it seems it's slightly moderate. In this video, we'll discuss the issue of autocorrelation. Often financial market returns are serially correlated, and that leads to issue of autocorrelation in error terms. A very simple test is Durbin-Watson test, which is, you can see the more detail about Durbin-Watson test with this DW test question mark command, as we have been doing earlier. You can read more about it. Let's implement this DW test command, Durbin-Watson test. So while implementing the DW test command, we need to supply it with the fitted object, which is SLR. Recall the object to SLR. If I run this command, notice that we get a true autocorrelation p-value as very high p-value, which means it is not significant, and DW statistic is close to 2. So we are not able to reject the null based on this p-value. That means as per this test, we have zero autocorrelation. Now please note, if DW value statistic is close to 2, then there is no correlation. If it is close to 0, then there is a positive correlation. If it is much more than 2, then there is a negative autocorrelation. Here it seems it's very close to 2, which is also indicated by p-value. That means we are not able to reject the null, that there is no autocorrelation. However, there is another very interesting test, which is Bruce-Godfrey test, for which you can see more details here with the BG test. So you can run the BG test and question mark and see all the details here. With Bruce-Godfrey test, let's see the issue of autocorrelation and how it affects our model. So we need to simply type BG test command and supply the model. By default, it will consider only one lag of error. So with one lag, notice there is no autocorrelation as per p-value. The BG test is statistic, which is essentially the LM test. And notice the p-value is not significant. That means we are not able to reject the null. However, please remember, many times the correlation is not because of the first lag. It can be also because of lags with the later periods, maybe second or third lag. To account for that, one can simply put the model with higher lag terms. For example, I can specify the order as 4 and see if the error term we have. Oh, so we are able to catch some serial correlation with 4 lags. That means there is some autocorrelation or serial correlation with higher order lag terms. To resolve this issue, one simple solution with the model is to add lags of returns in such model when there is serial correlation. In financial markets, a very simple and easily available solution is to add the lags of returns. In this case, maybe lags of market returns or lags of ABC returns, and see whether then issue of serial correlation is resolved. To summarize, in this video, we conducted Durbin-Watson test and BG test of autocorrelation. It seems with DW test and first lag Bruce-Godfrey BG test, we are not able to find any serial correlation, but when we examine the higher order lags with BG test, we find some evidence of serial autocorrelation. In practical situations, to account for such serial autocorrelation, one can add lag of returns such as ABC stock returns or maybe market Nifty returns lags to see if the serial autocorrelation issue is resolved. In this video, we'll discuss the application of robust standard errors. Recall our previous discussion on heteroskedasticity and autocorrelation. These issues afflict standard errors, and standard errors go into the model t values with coefficient divided by standard errors, which result in t values under or over. So under or overvalued standard errors can affect the estimation by resulting in lower or higher t values. One solution that has been developed is to create robust standard errors that account for issues such as heteroskedasticity and autocorrelation. Now with R, there are various flavors of these robust standard errors. We'll discuss the 4 most prominent ones often employed in computation of standard error, the routines that are often employed. And please note, it will not affect the coefficient estimate, but it will provide us with the robust standard errors that will go into the computation of t values that are arguably robust against issues such as heteroskedasticity and autocorrelation. So one way to compute is to use HCCM. So we'll simply use our fitted object SLR, and then we'll supply with the variance covariance matrix, which is HCCM. If you want to know what HCCM does, you can type question mark HCCM, and it provides you with the heteroskedasticity corrected covariance matrices. So if you run this, you will find the coefficients. Coefficient will remain same, but the standard errors will be changed, and they will correct the t values for heteroskedasticity corrected covariances. Similarly, we can also correct for heteroskedasticity and autocorrelation correction through VCOV HAC. This is for heteroskedasticity and autocorrelation. These are part of sandwich matrix. So you will generate another coefficient matrix with its t values and p values. You can also correct simply for heteroskedasticity depending upon the nature of whichever issue is affecting the model more. You can choose that. So VCOV HC. This will correct for heteroskedasticity only. And then there is Newey White correction. So lastly, we have Newey West White's correction. We simply type Newey West White correction, and if you run this, you'll find the Newey West covariance matrix estimation. All the discussion is here, but for implementation, we'll use the same notation, only that instead of VCOV HAC, we'll supply with the Newey West correction, and there we can obtain the corrected standard errors and the resulting t values. So with this, in this manner, we can apply the robust standard errors. There are various flavors available. We can check more about them with this coef_test command, coef_test. We can check more about them, different variants, different flavors, how to apply. All the flavors are available. We can read more about this. The four most prominent we have discussed: HCCM, heteroskedasticity corrected, variance heteroskedasticity and autocorrelation corrected, Newey West correction, and so on. So we can apply them to observe if there are significant changes in t values from our original values. It seems still applying all the robust standard errors, our coefficient is still very significant. To summarize, in this video we discussed the application of robust standard errors in correcting for issues such as heteroskedasticity and autocorrelation. We discussed four very prominent flavors of variance covariance matrices, that is HCCM, VCOV HAC, VCOV HC, and Newey West routines for correcting the standard errors in the model. Now that we have trained our simple linear regression algorithm and tested it for various econometric issues, we'll try to do some prediction using the test data. So we'll do some prediction using the test data. As a first step, we'll create a prediction object. Let's call it predict, PRED, and we'll assign the predicted values. We'll use our fitted object SLR, and we'll supply the new data, which is test data, and assign the values to our predict object. As a first step, let us visualize this along with the actual test data. So we'll plot along with the date, we'll plot our actual returns that are there in the test data. So this is test data, ABC returns. We'll be plotting them. So on x-axis we have date, and on y-axis we'll have ABC returns. Or rather, let us call returns. We'll use central object as predicted returns versus actual returns. Now we would like to restrict our graph for y limit. We would like to visualize from -0.2 to +0.2, which is a reasonable limit to visualize daily data. You would not expect returns to vary too much from 20%, more than 20%. Then PCH20 will ensure that our objects are plotted as solid dots. We want them to plot in red colors. Also, let us specify the type as line L, type L. So there will be a solid line, in fact. Now, along with BC returns, we would also like to have our predicted object plotted along the date. So again on the x-axis we have date, and on y-axis we would like our predict object, line width of 1. Let us specify the line width of 1 here also, although it's not necessarily needed, but just for information you can change it to 2 or any other number if you want it more or different, the width to be higher or something. So first let us plot this, let us plot using this command. Let's see if we are getting the object right or we are getting some error. So this object has worked. So this is the, currently in red we have the actual returns in the test data. We'll add some lines, these lines, we add some lines with this command. So we'll run this lines command, and these green ones are the predicted ones. This is our predict PRED object, predict object. Now to make it more aesthetically clear, I'll also add the legend here. So legend, let's put the legend on the top right. I see a lot of empty space, so I'll put the legend on the top right. And notice, you can see that in our window, minus 0.2 to plus 0.2, sufficient amount of gap is there. So if I would have put it minus 1 to plus 1 or some higher number, it would have looked not so aesthetically good. So right now it is decent, the window is decent. In fact, I can put it as minus 0.1 also, that would be okay as well. So if I run it for minus 0.1 to 0.1, that also looks better. Now I'll add the legend on the top right part of it. So we have actual return and we have predicted return, and we like to provide the fill. So here the actual return is in red as we noted earlier, and predicted one is in green. So I'll add the green here, and then we'll run our plot. And we have the complete diagram here. Let's examine the full diagram. Notice it seems that where the green one is reasonably capturing, not in terms of amplitude but in terms of fluctuation, where the fluctuations are higher in the red ones, fluctuations are also higher in the green ones. So there is reasonable similarity in the movement. However, we need more statistical evidence to conclude that, and for that we will use our correlation command. We'll use the core command to test whether our predicted returns and actual ABC returns. So this is actual ABC return and this is our pred object. Let's examine the correlation, and the correlation is reasonably high. So this is 0.43, that's almost 43.78%. So we are able to capture the dynamics of the ABC returns to the extent of 43.78% using our regression, simple linear regression algorithm. So to summarize this video, we created a predict object, then we plotted this predicted object along with our actual returns contained in the test data that we created. The dynamics appear to be reasonably similar. That means we are able to capture a lot of dynamics of actual return in our predicted object. We statistically examined this with our correlation measure. We checked the correlation between actual return and predicted returns. There is almost 43.8% correlation between these two entities. So it seems that our prediction algorithm has done a reasonably good job. In daily data context, this is a very high level of prediction efficiency. In this video, we'll discuss the computation and examination of out of sample fit or accuracy of our prediction algorithm. Please note that you need some kind of cost or error function to compare the model across various competing models or algorithms. Now there are various cost functions and error functions that can be employed, starting from very simple models such as MSE or RMSE errors to more complex functions. Now let us examine how to execute this in R, and for that we need library matrix, which provides us with a number of such error functions to compute. for all, let's start with this MSE. MSE computes the average square difference between two numeric vectors. So if you want to compute MSE with matrix library, you can simply type MSE test $ABC. So this is our actual return object and along with the predicted object, and you can compute the MSE measure. Now on its own, on a standalone basis, it does not have any meaning. You need some other competing model and you would like to compare this MSE, that is the average square difference between the vectors, to compare. Another variant of this error could be RMSE. RMSE computes the root mean squared error between two vectors, like we have here two returns, ABC return and actual ABC returns in the test data and its predicted values. Also, if you want to read more or know more about these measures, you have to simply type $RMSE and you'll get most of the information here. You can check on the internet also, but most of the information relevant here can be obtained from the help window. Now to implement that RMSE in R, you simply need to type RMSE and then test $ABC, and then you have predicted object. You can compute this measure and then you can compare this measure with other competing algorithms or models. If you may have various other competing models, maybe multiple linear regression or some other variables you want to test, and then you can put it against this value of RMSE. Then another important measure you have RAE. RAE computes the relative absolute error between two numeric vectors. So again, to compute the RAE, you have to just type RAE. And please remember, these are cost or error functions that help you understand the out of sample fit. Why we are saying out of sample? Because we are using it on test data, not on the data where we trained the algorithm. So again, we'll type test $ABC, which is our actual data along with the predicted object, and we can compute this measure of error as well. On their own, standalone basis, they do not make much sense. You need to have a competing model or competing algorithm to compare with. Then you have MAE error also. MAE computes the average absolute difference between two numeric vectors. So again, the computation method is same, the implementation is same. We use test $ABC along with the predicted object, and you get the number here in the output in the console window. Similarly, you have MAPE, another very important and famous measure, MAPE of error, which is MAPE computes the average absolute percent difference between two numeric vectors. If you want to compute the MAPE, you can simply type MAPE test $ABC and you have predict object. You can compute MAPE also. Then there are a number of measures. For example, you have SMAPE. SMAPE is basically, it computes the symmetric mean absolute percentage error between two vectors. So you can compute SMAPE for test $ABC data with predict data. You get that number. In a similar manner, there are other measures, we can compute them. For example, you have MSLE. MSLE computes the average of squared log error between two numeric vectors. The computation method remains the same. Then you have RMSLE. RMSLE computes the root mean squared log error between two vectors. Similarly, you have bias measure. Bias measure computes the average amount that is actual greater than predicted. You can compute in bias in the percentage form also. You have RSE measure. RSE measure computes relative squared error between two vectors. For example, you can simply type RSE test $ABC along with predict object. Same, the syntax remains the same and you can get the RSE object. You can also have RRSE, which is the root relative squared error between the two vectors, and so on. You can there are many measures. These were the most important ones. You can pick a number of measures and then compare this matrix along with another matrix. You can create more complex objects. For example, you can give different weights to these different errors and then create a new object as per your requirement, or some more complex expression you can create out of all these error objects and create a more complex error object to compare against competing models. So there are different flavors to it available with you. You can use them to check the out of sample accuracy of your model. To summarize this video, we discussed a number of error or cost measures to examine the out of sample forecasting or prediction accuracy of our trained algorithm. We also saw their implementation in R, and we noted that we can create more complex forms of error or cost functions by assigning weights or some complex expressions to these readily available error or cost functions. In this video, we'll start with multiple linear regression model. Most of the syntax to implement and execute the model will remain same. So let's call it MLR, multiple linear regression model. And as we did with the simple linear regression model, we'll use LM object, ABC returns, and let us add sensex returns, BSC sensex, sentiment measure. Since this is a multiple linear regression model, we'll be using a number of variables on the dependent side, Nifty, dividend announce, dividend, and we'll use our train data set to train the model. So now that we have put the expression, we have provided the expression, let us run it. Our object, MLR object, saves the entire output. So let us print the output summary object MLR. Let's call it model. Again, we are using the same naming convention. Let's see this output. Let us examine the output of this model. Notice the coefficient of Sensex and Nifty, both are broad market indices, while Sensex is heavily significant at 3 star, that is significant even at 1% level. Nifty is turning out to be negative now. This is slightly surprising for us because we already saw that Nifty with simple linear regression model, that Nifty also has a positive impact. Now this, and here Nifty is not significant, this suggests that there is some possibility of issue of multicollinearity, as we'll examine in the next video. Because Sensex and Nifty both are market-wide variable, so this provides us intuition of multicollinearity issue, that because of that the coefficient and significance estimation of Nifty is getting affected. We'll examine that later. Also notice that sentiment variable is turning out to be a very significant, very significant even at 1% level, that means 99% confidence. Dividend announce is also significant. It is turning out to be at 95% confidence or 5% significance level, as we can see here, significance quotes. So dividend announced is also very significant. Notice the adjusted R square, the power of model is very high as compared to the around 10% that we saw with the simple linear regression model. This is for the fact that there are a number of significant variables that have been added. So the overall power of model to explain the variation in returns is increased considerably to around 27.84%. However, we still need to observe the issue of multicollinearity here to resolve that. To summarize, in this video, we trained our multiple linear regression algorithm using the trained data. We summarized the output and briefly reviewed the output. In the next video, we'll jump to the resolving multicollinearity issue as we discussed in this video. We'll skip residual diagnostic, issue of heteroskedasticity, autocorrelation, and robust standard errors, because they are exactly identical to what we have already seen in the simple linear regression model. Same commands with same notations will be employed, and the examination will be done in an identical manner. So in the interest of time and brevity, we'll skip that part. We can directly apply the same codes here. Same exactly identical codes can be applied for the multiple linear regression model to obtain and examine the residual diagnostic, heteroskedasticity, autocorrelation, and robust standard errors related discussion. For more detail, we can directly look to the video topics on heteroskedasticity, autocorrelation, residual diagnostics, and robust standard errors video topics to get more information on this. In continuation with our last video, we noted that the issue of multicollinearity may afflict our estimation process, and therefore in this video, we'll examine the issue of multicollinearity in more detail. Please recall, we said that there's a possibility that some of the independent variables may be correlated, and therefore that may give rise to the issue of multicollinearity. So as a preliminary evidence or examination, we'll try and compute the correlation in the trained data set for the independent variables. Our independent variables include ABC, returns, sensex, and we'll see which of these variables are heavily correlated. These are all independent variables that we employed in the multiple regression model. These are the main variables. We are leaving the dividend announced variable, which is a dummy variable, so chances of this variable being correlated are very low. This is the dividend announced is just ones and zeros. So notice the correlation matrix that we have produced here in console, and notice the very high correlation. So between Nifty and Sensex, the correlation is almost 80%, which is a clear indication that there is a possibility of multicollinearity because of this high correlation between Sensex and Nifty. All the other variables are though correlated, but the levels are even lower than 50%, much lower than 50%. So they may not have much multicollinearity related effect. So let's also recall that we created our model object MLR in which we trained the algorithm. So we'll use this what is called VIF, variance inflation factor, what we call variance inflation factor, VIF, which measures the extent of multicollinearity in a model. So we'll use VIF and MLR. If this number, and it indicates variance inflation factor for different variables in the model. If the number is around 1, then multicollinearity is almost negligible. If it is higher than 2, then it is moderate. If it is higher than 5, then it is really high. Notice the multicollinearity with Sensex and Nifty variable, and both of them are heavily correlated, is 2.9, which is on the higher side, which indicates that we have to drop one variable to remove the multicollinearity issue in the model. Now that we have seen our model contains the issue of multicollinearity because of the market variables Sensex and Nifty, we would like to remove one of these variables to improve our estimation. And in the interest of that, we'll again train our model on the train data, but this time we'll remove one of the market variables and run our regression ABC on Sensex. So we are removing the Nifty. So we are only running on Sensex, sentiment plus dividend announced, and we'll again use our train data. Let us run this model and let's summarize this into a model object. So we'll create a model object in which we'll put our summary of the model. We'll print this model object, and again the adjusted R-square numbers are same, but notice the Sensex has much higher significance as compared to earlier. The beta, which is the coefficient of Sensex, is around 0.55. Sentiment variable is also very significant, and dividend announced is very significant. To interpret the Sensex variable, for example, 1% increase in market or Sensex leads to 0.55% increase in the ABC returns. Also, notice the dividend announced variable. Since it is a dummy variable, on average, there is a difference in return when the dividends announced. There is increase in return of about 0.0038% on that dividend announcement day, and the model is able to explain around 27.85% of the variation in the ABC returns. So we have improved our model and accounted for the issue of multicollinearity. To summarize this video, we noted that when we computed the correlation matrix, we found that the two market variables, that is Nifty and Sensex, were heavily correlated with a correlation number of almost 80%, and indicated the presence of chances of multicollinearity, which we further examined with our variance inflation factor, which is VIF. And VIF suggested that indeed Sensex and Nifty variables are afflicted by the issue of multicollinearity. So we removed the Nifty variable and then again trained our model, and the model output is reviewed in the discussion. In the next video, we'll create a predict object and we'll compare the predicted and actual test values and try to visualize them to see our out of sample forecasting efficiency. In this video, we'll create a prediction object using our test data with our trained algorithm, multiple linear regression algorithm. So we'll create a prediction object with test data. The procedure is very similar to what we did with simple linear regression model. We'll create a predict object. We'll assign the values that are predicted using MLR. This is MLR object that we have already trained object, and in the new data we will assign the test data set. So we are assigning the prediction object, creating a prediction object with the test data. Now that we have created this object, we'll try and compute the correlation between this predicted object and our actual ABC returns. So we'll use this predict object and we'll compute the correlation between predict and test, and there's a 57% correlation. Let us also try and visualize, make a comparison using visualization. So we'll first plot our actual returns. We have already seen these commands with the simple linear regression model, but still we'll run them again. So test $date, test $ABC. So with this xlab, again the same syntax, date, ylab as returns. We'll be plotting actual and predicted returns. So the central heading again here is actual versus predicted returns. Again, we would like to see the y-lim here, so we would like to set the y-limits from minus 20%, which is a reasonable limit, to plus 0.20. We would like to plot red color line as actual ABC returns in the test data and type as line. So this is our line type. We'll run this later with the complete thing. Next, we would like to have lines command. With the help of lines command, we'll add our predicted object. So let's call it predicted object that we have just created, and color we'll give it green. Again, the type, will assign a type of line. So we are using line type. Other option is to plot in terms of points. For this kind of graph, line type is more preferable to make a better comparison. Again, we'll add legend. So like we did last time, we'll use legend on the top right side. On the top right side we have legend, and we have actual returns first, then we have predicted return. We'll assign colors, so fill equal to, we have red as actual and green as predicted, as we have noted. So now let's do some plotting here. So I'll enlarge the plotting window for better visualization. First I'll run the main plot command. So these are my actual returns in red. Then I'll add the lines. Through lines command I'll add the predicted returns, and then I'll add the legend. Now let's zoom this graph and notice very nicely our object is capturing. As we also saw in the correlation, there was a very high correlation, and the same is reflected here. Our predicted object in green is very nicely capturing the fluctuations in red, actual returns, ABC returns. So that means our multiple linear regression algorithm has done a very nice job of predicting the returns, and that was also reflected in our very heavy correlation of 57.7% between actual and predicted returns. To summarize, in this video we created a predict object using our test data. In this predicted object we computed the correlation with the actual test data. The correlation is 57.7%, which was very high. We also plotted and visualized the actual return and superimposed them with the predicted returns, which again confirmed that our prediction has been, the algorithm has been very efficient in predicting the objects. Now here we are not doing the out of sample forecasting errors that we did for simple linear regression model. We can go and review the video on out of sample regression forecasting video topic. In that video topic on out of sample error forecasting, we have discussed in great detail the R implementation and the interpretation of error functions. So in the interest of time and brevity, we will not repeat there. The command, execution and discussion remains identical. So we can refer to that video topic on out of sample forecasting. To summarize this lesson, we model ABC stock prices using simple regression problem with market index variable. The model is trained using training dataset and various goodness of fit measures are examined. The fitted model is examined visually as well. The model is tested using test dataset and various measures of out of sample fit are also examined. Next, a multiple linear regression model is trained using trained dataset on multiple variables. The fitted model is visually examined and also various goodness of fit measures are examined as well. The model is evaluated on various issues related to multicollinearity, heteroskedasticity, and autocorrelation. Lastly, the model is examined on various parameters for its out-of-sample fit performance.